Hello there. Welcome to another problem session. So today we have a very important problem. Actually, it's a set of problems, and you should understand how it works in detail, and also the final result that the like a radius in this situation, this formula here, that radius the orbit is that, because it has a lot of uses. So for instance, this particle at this instant is here, but it will, if you follow it, it will, according to this, this particle will actually go in a circle whose radius is depends on the charge to mass ratio and the speed. So you can see how, if you set it up, you can if you know the mass of the particle, get the charge of the particle. If you know charge particle, get the mass of the particle. So if you measure r and you have set up a magnetic field, so some magnetic field you have set it up. So this is the North Pole and this is the South Pole in this example, that way, and this is a uniform magnetic field around here. So this B over V, if you know what speed this is going in, because we will say what is called a speed selector. So over here you had a particle and there was a mechanism in which a particle had come out with this particular speed and entered this region. So you could actually inject the particle here at a particular speed. So this speed can be known, okay, from before. We're going to talk later about how to know the speed. So this is known from experiment. So you get some kind of track, and you know this from setting it up, and you know how you set it up. So this will be known, so you can get mass of a charge from here. And so if you know the charge of the particle is 1 unit of like electric charge, something like that, of electron, 1 electron charge, then you can figure out the mass of the particle. And this is how lots of particle physics was done for a long time, and it's still one of the really basic mechanism by which we figure out what the mass of a particle will be from the tracks it makes in between the magnetic field. So this is an important problem, and it's an important result to somehow either memorize it or able to derive it on the spot, So what's this problem? Let's go a little bit. So this is the figure that goes with the problem. So a particle of charge Q and mass M at t equals 0 is moving in the direction perpendicular to the magnetic field. That's what this whole thing is. And the speed at that instant is v. So several things we're supposed to find. Actually, the b should be a. We're going to do a first, and then we're going to do that. So the speed of the particle does not change. You can show that the speed of the particle doesn't change, and we will will show that the way F equals ma works out is the only thing that changes the direction of the velocity, not its speed. Okay. So there is acceleration, but only it shows up in the direction change of the velocity. So the moves in a circular radius. So this will become a circular motion in this case. The part D is what happens when this particle, when initially it's not that way, but if this is the XY plane and this is the Z axis, this is the B direction, maybe at that point, maybe velocity is pointed that way. Maybe there's an angle theta here, velocity pointed that way. Then what will happen? And you don't have to redo a whole thing from what you have done here. You should be able to deduce it in a very short order what this will look like. Okay. All right, so let me give you some time to work on it, and then you can pause this video and come back and try to understand how I explained this thing. Okay, so I'm going to erase all of this and set up the problem. Okay, so first we want to set it up at arbitrary instant of time. So say at an arbitrary instant of time, velocity b, which can be written as x component, y component, and z component. Then you can write that Newton's equation of motion. So we are going to do Newton's equation of motion because I'm going to assume the speed is much less than the speed of light. Okay, I'm not going to do relativistic treatment. Okay, so and this is most of the time we are dealing with this, and there's no need to complicate more than what necessary. Okay, so what you're going to get is m dv dt. This is the acceleration, mass times acceleration, that's what that is equal to charge q and v cross b. So this is the magnetic force. So this is at arbitrary time. I don't know it's going to come off the plane or something like that, but I only know at t equal to 0 so like that. So I have to solve this for when v at 0 instant is just along the x-axis, nothing along the z-axis. That's what at 0. And also we're given that position is at the origin at the 0 time, t equal to 0, and this is t equal to 0 is all 0. Okay, so that's what's given, and you're supposed to solve this problem. And it's because there's a cross product, it is going to be a little bit of difficulty in setting it up, right? So let's look at what's going to be. So you have a q and v is a I hat vx plus j hat vy plus k hat vz, right, on the right side. And then you have a b is all along k hat, so b is just k hat. So this whole thing is just turns out to be I hat cross k hat, j hat cross k hat, and k hat cross k hat. This will give me 0, but I hat put k hat will give me minus j hat b times vx, and this will give j hat cross k hat give me plus I hat b vy, and then plus 0. You know, this gonna get 0. And on the other side, I'm gonna get on this side, let me erase. And on this side, I'm going to get m vx I hat plus vy j hat plus vz k hat. So you can see I can just equate them. So let's get the m out of the way, get the b's out of the way, and this quantity I'm gonna have one symbol. I'm gonna call it qb over m, m on the qb over m. So it's just a simple writing, one symbol rather than the whole combination of things. So So I got Vx I hat with I hat. So I get Vx time derivative. So dot equals to ddt for simplicity. So Vx dot is going to be equal to minus omega, actually omega times Vy. Omega times Vy. Vy dot is going to be j hat with a j hat, then comes to minus omega Vx. And Vz hat, this is the acceleration along the z axis, is actually 0. That means this just simply means if Vz at 0 is 0, then Vz at any time is 0. So this is already, there will be, which means it's going to be, this means in our case, where this is the situation, motion will be confined to the xy plane, which is perpendicular to the b direction, right, in this example. So we need to solve these. You can actually solve quite different ways. So let's look at a very simple one. Say I take a time derivative of this. So I get a Vx double dot omega Vy dot, and then I can use this guy, and so this guy omega minus omega Vx, and so this is minus omega square Vx. So Vx double dot is like that. So this is a very famous equation, and this is the equation that you deal with when you have a mass attached to a spring. So this has a very simple answer. Vx at t is some constant a1 cosine omega t plus some constant a2 sine omega t. So this equation, this is some quantity a double dot equal to minus some alpha square a. This is a very important problem, and this is simple harmonic motion, and if you want to call it x, you can just call it x being unknown. This is the way it's, and sometimes it's kind of, we just use a little omega square. We want to have a square because we want this to be positive, this quantity to be positive. So that's it's a positive quantity, and we want to express this positive quantity, and we want to square because of when you take a 2 time derivative, each time one of these is going to come out and it's going to be squared. So this is unknown constants. Let's do other way around. Take a time derivative of this guy, and you have Vx dot, put in here. So it's going to be exactly the same kind of equation, minus omega square Vy as well. And this is going to have its own Vy of t is going to be maybe some other constant, a3 cosine omega t plus a4 sine omega t. But you know, all these a's are not totally independent. Okay. All right. So, but if you look at the Vx dot, has to be proportional to this. If you take a dot of this, has to be proportional to that. So let's do the Vx dot here, and so Vx dot should be omega times that. So Vx dot 1 over omega should be equal to the same thing. So this should be equal to each other. So let's do it. And thus if you take a time derivative of this, it's going to minus omega omega a1 sine omega t, and this omega go away actually, because of this dot that's going to kill the omega, and then this will be a2 cosine omega t. So it's going to be like that. And now you compare sines and cosines, so this will go with that and that will go with that. So a3 will equals to a2 and a4 equals to minus a1. So we can just keep a1 and a2 as our unknowns. So we have a Vx of t is a1 cosine omega t plus a2 sine omega t, but Vy of t is a3 is a2 cosine omega t minus a1 sine omega t. Okay, now we have initial conditions. So at t equal to 0, this should be v, and this should be, this will go away. T equal to 0, sine 0 is 0, so this is going to just leave a1, and this will be this will here, let's see, at t equal to 0, this goes away, and this is a2, so this is equal to a2. So a2 is 0, a1 is this. In under this condition, we have even simpler formula. Okay, so let's clean up and let's see what we get. Okay, so this is what we got after putting in for a1 and a2 in the two expressions. From here you can immediately see that at an arbitrary time t, speed square, speed is speed at time t is equal to square root of vxt square plus vyt square plus vzt square. Now this is 0, so this plus this, you can see that this is equal to simply square root of v times cosine square omega t plus sine square omega t, and this is just some angle, you know, and if this, you call this theta, then this is equal to 1, and so this is equal to v, original speed, independent of t. So one of the question was that the speed of this thing does not change. Speed remains constant. That just means this very important thing, that if you put a particle in a magnetic field, then its kinetic energy is not changing, right? That means kinetic energy is independent of time, does not change. That means the magnetic force does not do any work on a moving charged particle. And this comes from work energy theorem, right? Work energy theorem. So these are some of the things, but you know that when you have a magnet, you can pull it, you can make it accelerate and increase its velocity, right? So say you had a north pole here and south pole here, so this is some magnetic field here, and you bring a tiny magnet and it's north pole this side and the south pole this side, and so this one is v equal to 0 and this v not equal to 0. So you know speed increases for a magnet. But if you have a charged particle plus q and you shoot it in here and it's v, that v doesn't, it can change the trajectory, that v is same as v. So unlike the magnet, work done on a charged particle is actually zero, but work done on a magnet is not zero, and that's actually a little bit different mechanism. But you should be aware that when people say magnetic field doesn't do any work, that's actually not a complete picture. Magnetic field does work on a magnet, magnetic dipole, but on a charged particle, it does not do any work. So that's a clarification of this. Okay, let's clean this up and see we can do other parts. Okay, so B and C are about position and trajectory. So we want to find at t equals 0 is like this. X of t, y of t, of z of t. Of course, this is equal to 0 because since we figured out vz of t equal to 0, right? So it's position z and z of 0 is 0. So it's always going to be. So we need to figure this out. Let's look at how we're going to do say xt. So vx of t is dx dt. So this one is going to be v is constant cosine omega t. So we can integrate it, and so x of t minus x at 0 is going to be x of t minus x of 0 is going to be v over v over omega sine omega t, and this is 0 to t, and so this is just a v over omega sine omega t, and this is 0 because this is 0, this is x of 0, and this is y of 0, and this is z of 0. That's taken to be at the initial time. It's at the origin of this coordinate system we have picked up. So we've got x of t, pretty cool, and that just v of omega sine omega t. Let's do y of t same way. So dy dt is equals to minus v sine omega t. Okay, this will integrate y of t minus y of 0 equals to v over omega cosine omega t. 0 to t is v over omega cosine omega t minus v over omega, and this is 0. So y of t minus v of omega equals to v over omega cosine omega t. This is 1, and this is 2, and this is 3. So we done one of them. Those are the equations. Okay. For the other one, to show that this is a circular motion, so to show circular motion, to show it is a circular motion, what we're going to do? Well, we're going to take a 1 and 2. We're going to square and add them. What do I mean? I mean xt square plus, we're going to do this, not so isolated this guy, so we will get a sine square plus cosine square. That's why I isolated that. And this is y of t minus v of omega square equals to v square over omega square sine square omega t plus cosine square omega t, and this thing is 1. So this is the equation of a circle whose Let's look at what the origin is and what the radius is. Okay, so I was just copying it and I realized that this should be a plus, because when this thing comes on the other side, and this was y of t, when this thing comes on the other side, it becomes a plus. Okay, so this is a plus. So if I look at x, y, x and y, this plane will look at this plane. So it's going to be this is x minus 0 square, right? So this is the center, this, and this is y minus y0. So it's going to be y so this is y0, y center, and this is the x center. You have subtract there, so y center is minus v over omega, and it was here, and this is the center, and it's going like this at t equal to 0. So this is on the other side, this is the radius v over omega, and so it seems like it's gonna go the diameter over 2 v over omega, so this another v over omega, and so it's going to go in a circle like that. So it's a circle with center is over there, and so it's going over here, so it's going to move like that. And make sure that this so at this point it seemed like acceleration is that point, right? When it's t equal to 0, velocity is this way and must be acceleration this way. Let's check that out, because the positive charge is going that way. So if I go this way, so it's a if you go from the velocity to the b direction, acceleration is pointed towards me. So in this figure, I noticed that acceleration is pointed in that direction. Acceleration, and sure enough, it shows the negative direction. So this is correct. So this is the way it's going. Okay, so we have proven that it is going in a circle. We figure out what the radius is. So the radius of the center of the circle is at 0 minus v over omega. 0. This is the z coordinate, but this is the xy plane, so I don't have to worry about that. And the radius of this circle is v over omega. And omega, we had already did that, so this is mv over q times b. Okay. Now we want to address what happens when this thing is not that way, but b is the x-axis, is the y-axis, z-axis, and this is where the b is, but the v is pointed this way, and there's angle theta between them. Okay, so let's do that out without doing a whole bunch of work. And for simplicity, I'm going to say that at t equals 0 is an xz plane. For simplicity, so this is the x direction, and this is the z direction, and the v is pointed in the this plane, the angle theta, and the y direction is that. But this is in the xz plane. So this v is in the xz plane. So it was at t equal to 0. So the v, instead of that, is going to be v of 0 is going to be v sine theta for the x, v sine theta for the x, nothing for the y, and v cosine theta, right? Now, if you go back in this equation, from there you know that dvz dt will be 0. Why? Because b is in the direction of k hat, so there can't be any force in that direction because force is cross product, so it's going to be perpendicular to this, perpendicular to both of these vectors. So it's not going to be in, there will be no force along the k direction. So this means that Vz at any time t equal to Vz at 0. This means that's going to be just V cosine theta. The z of t, it will be z at 0 plus V, this is constant, so Vt times cosine theta, that's it. So that's, and this is 0. So it turns out the z if t increases linearly, so the z-axis increases linearly. And how about the other things? Well, this is, as far the xy plane is concerned, instead of all this v, we have a v sine theta. So the over here we're going to have a all of this formula will be exactly identical. We'll have a Vx will Ft will be V sine theta cosine omega t. Vy of t will simply be V sine theta minus V sine theta sine omega t. And how about these guys? These guys will be very simply x of t will be V sine theta over omega sine omega t, and y of t simply will be V sine theta minus V sine theta over omega plus V sine theta over omega cosine omega t. So these are the answers. So it's still going, the projection of this in the xy plane is still going in a circle, but that plane is getting lifted, and that is what the helical motion will be. Let me draw this out. So if you draw at, say, sometime t0, sometime t1, sometime t2, so it's still going in a circle in the xy plane. If you look down at the projection, is still a circle, xy plane, but then this plane actually is moving with the rate it is moving is the z coordinate. Z equals to V cosine theta times t. So it's the z-axis is moving at with time. Okay, so this is the helical path, and you can say after what time it was here, then over how long it takes before it comes back here. So you can see that this thing to go in once around, once means it's going with an omega here, right? So it's going to be 2 pi over omega. So that's the delta t. And in that delta t, how much distance it was covered, that delta z. So that delta z covered will go with this. It will be going with this pitch v cosine theta. That's the projection along the z-axis, okay? Times this delta t, 2 pi over omega. So this is once around. This once, often people ask this question, that how long will it take before it comes back to the same point in xy plane, okay? And it's how much distance along the z-axis it would have moved, and you can figure that out by knowing that z is moving at this rate, and so you have to figure out how much time it takes to go once around. And going once around is just a circular motion at this angular velocity. That angular velocity means the time is 2 pi over omega to go once around. Of course, the twice around will be 2 times that and things like that. And then once you know once time around time, you just use that time to, and the z velocity is speed in the z direction or z velocity. And that tells you what's the pitch. So this is also called pitch of the helix. It's like it's repeating, this helix is repeating this distance in the z-axis. Okay, I think this is a very important and good problem to master. So there are a lot of things here, cross products, how to set up F equals ma, how to combine equations, how to read the circular motion, lots of little nice trigonometry and some three-dimensional thinking. So a lot of things went in here. If you haven't subscribed, please subscribe. And if you got something out of what I just said, hit the like button. If you like this kind of way of thinking about physics, there's more in this website. That's my website I maintain, and I'm continuously trying to improve that website. Okay, I think that's it for now. Take care and bye.